So could you please tell us about who you are?
Hi, my name is Nicholas Lee. I'm a research engineer at Stanford University in aerospace engineering. So what I do at Stanford is I study the space environment and satellite systems. We look at small spacecraft and we look at how the space environment affects satellites. In particular, one of the things we've been looking at are meteoroids. We were very interested in what happens when meteoroids hit spacecraft, as well as when they enter the atmosphere. So we've done things like experiments in ground-based facilities where we shoot particles at really high speeds and look at the plasma that's formed when it hits a spacecraft surface in our vacuum chamber on the ground. And the other thing we've been doing is using large radar facilities to study meteors that burn up in the atmosphere.
And why did you want to become an aerospace engineer?
I've always been interested in space. When I was 6, my parents took me to Florida for the first time, and we visited the Kennedy Space Center. So I got to see all of the rockets there, the vehicle assembly building. So from that age, and even before that, I was really interested in just technical things like cars and trucks, and got into airplanes, and seeing that really sort of was a formative experience. And then eventually I discovered Star Trek, and just watching the show and seeing what humanity could achieve if we were able to get out into this galaxy and explore other planets. It just really excites me. And also, it is an optimistic vision for humanity that I really believe in. So Star Trek really forms the core of what I see humanity being able to achieve if we do the right things now. And so I'm sort of trying to do my part to get us towards that future.
Mhm. And why did you choose to specialize in meteors and satellites?
That was sort of a lucky, or it wasn't so much in my plan. When I did my undergraduate studies, so I did my bachelor's degree in Toronto. One of the things we got to do for our senior design project was to build or to work with engineers at MDA, which builds the Canadarm, the Space Station Canadarm. They, at the time, were working on a concept for robotically servicing the Hubble Space Telescope.
Mhm.
So that was right after, a couple years after Columbia happened. So Columbia had been hit by a piece of foam when it launched, and then when it came down, it broke up. And at the time, for a period of a few years, they had shut down the space shuttle program, and they were saying, we're not going to launch the shuttle to any place other than the space station. So that there was a lot of work that this was in 2004, 2005. There was a lot of study going into, can we send a robot, or can we send an autonomous vehicle up to the Hubble Space Telescope to do the repairs rather than sending a shuttle with human astronauts. So I was really excited about working in grad school on robotic servicing, on autonomous vehicles, things like that. And when I got to Stanford for my master's and PhD, the funding situation was just not where I needed it to be to pursue that. So I started looking at other topics. I was looking at solar sails, CubeSats. I ended up working in the CubeSat lab for a while. And eventually we hired a new professor, Professor Close, who was really interested in the meteors. And she had this open project on hypervelocity impacts, which was the ground-based studies looking at shooting things at tens of kilometers per second.
Mhm.
And so I started working with her and got more and more involved in her lab. And eventually that just sort of became the direction I took my PhD. And I ended up sort of applying a lot of the skills I had learned in my other research topics, but I ended up focusing on that more because it happened to be available at the time.
Mhm. And you also mentioned that you study the plasma distribution with meteorite impact. So how are you able to detect the plasma distribution?
Okay, so plasmas are often described as the fourth state of matter. So if you have any sort of material, if it's really cold or under high pressure, it's a solid, right? And then as you increase the energy, it becomes a liquid, and then eventually it evaporates into a gas. When it gets even more energy than that, whether it's through something like an impact event or because of energy being put into it through radio frequencies or light shining on it, there are many ways to make a plasma. What happens is you get electrons that pop off of the atoms that are part of the matter that you're working with. So you end up getting populations of negatively charged electrons and positively charged ions. And so because now you've got these electrostatic effects, you can manipulate the expanding gas cloud with electromagnetic fields or electrostatic fields. So what we do is we start with a piece of metal, basically an electrostatic probe. So it's a conductive surface that we put in front of the impact point, and we connect that piece of metal to an amplifier circuit that converts any electrical current deposited on the metal into a voltage that we can measure. So we put a couple of these sensors over the top of our point of impact, and then we put an electrical bias. So if we take our target and we charge it to a very negative potential, so we make it negative 300 volts, negative 1000 volts, what happens is we shoot a particle and it hits, and we end up with this very dense ball of plasma, which is positive ions, negative electrons. Because it's negative, because the target itself is negative, what happens is it repels the electrons and sucks up all the ions. So we get a jet of electrons that shoots out, and those electrons deposit onto our collector plate on the sensor. So we end up getting a negative current deposited on the sensor, which then converts into a voltage. If we bias the target to a positive potential, so we push it up to, let's say, 100 volts positive, then what happens is it sucks up all the electrons, and what it shoots out are all of the ions. Now, this is where it gets interesting, because the ions will be composed of all different masses. You'll have iron ions from the projectile we're shooting. We'll have silicon ions from the target, or aluminum, or whatever metal it is that we're hitting. So all of these will have lost one electron, because that's about how much energy we can kick off of it. So they all have the same charge, but they have different masses. And so when we have a constant bias, so we're shooting it down this 100 volt or 1000 volt potential well, the lighter ions will move out fastest, and then the heavier ions will come. And so on our sensor, what we see are, over a period of time, we see these different pulses, which correspond to the different elements of the plasma that have been separated.
Mm-hmm. And what are some of the problems that you're trying to solve with studying the plasma within the collisions?
So what we're really concerned about is the fact that when particles hit spacecraft, these plasma effects can result in electric discharges just from the electrons or ions moving in different ways. It can also result in radio frequency emission. So if you imagine the impact occurring on the target, and we have this little ball of positive and negative charge. If the spacecraft is charged the right way, either by the sun or by interaction with the Earth's magnetic field or the ambient solar wind plasma, there's a lot of ways that spacecraft can build up charge on their surface. If the right charge conditions occur, what we can do is create an electromagnetic pulse, or an EMP. So when this particle hits the spacecraft, it creates the plasma, it interacts with the surface charge, and then maybe it's a jet of electrons that shoots out. Maybe it's a plasma instability or a more complex phenomenon that we're trying to still figure out through our experiments and our simulations. So what we're concerned about is if there's this electromagnetic energy being radiated out of the point of impact, that's something that can go through the spacecraft wall and affect the electrical systems. We know that, for example, Cassini, the probe that's been out at Saturn and crossed through the ring planes, when it went through the ring and was impacted by a lot of different ring particles, its antennas were seeing an electrical effect. So it was able to detect the impacts of ring particles on the spacecraft itself. And we've seen that with a number of other spacecraft in different parts of the solar system. So we know there's a way impacts can create an electrical effect on the spacecraft. And the question is, can it create an electrical effect that we don't want? Something that's not just a scientific measurement, but maybe something that causes a spacecraft failure. And there's been a number of instances where spacecraft might have had that happen in Earth orbit, where in the peak of a meteor shower, all of a sudden its gyroscopes fail and it starts tumbling. That happened with the Olympus spacecraft, which was a communication satellite. It might have happened with one of the GOES Earth observation spacecraft. So it's something that doesn't happen often, but what we're basically worried about is the fact that with small particles being much more prevalent, much more frequent impacts than large particles, it's much more common for us to get small impacts that can create a small plasma and an electrical effect than for the large impacts that might actually punch a hole and break apart a spacecraft the way you might see in a movie.
Mm-hmm. And the conditions on Earth and between space are relatively different. And you also do ground-based hypervelocity impact experiments. So could you describe the experiment process on how you design these tests?
Yeah, so in space, obviously, meteoroids are just everywhere. Space debris is where it is. There's a lot more space debris this month than there was last month because of various things going on in Earth orbit when satellites break apart. And so those things are just out there. And when they hit at kilometers per second. So if you have debris in orbit, the typical impact speeds between a piece of debris in low Earth orbit, around 200 kilometers altitude, and a spacecraft is about 7 to 10 kilometers per second. So think about how fast that is compared to like a car or even a jet flying. Kilometers per second is extremely, extremely fast. And if you're looking at meteoroids coming from outside of the Earth's gravity well and falling into Earth's gravity before they hit a spacecraft, those particles hit at between 11 and 72 kilometers per second. So that's faster than the speed of sound in most materials that spacecraft are made out of. So how do we get speeds like that on Earth? There's several different ways we do that. And there's a number of specialized facilities that we use. We don't operate any of them ourselves, but at NASA Ames, which is the NASA center in the Bay Area in California, we've gone to their light gas gun facility. This is basically a gun that uses a gunpowder charge to ignite a piston. It compresses a hydrogen gas down a converging duct. So it basically sends a shockwave down that then impacts a particle and accelerates it down the gun barrel. And they can shoot milligram-sized particles up to about 5 to 7 kilometers per second. So it's basically representative of debris impacts. And basically, we take the gun, the facility people help us like clean the gun, assemble it. We put our sensors inside a big vacuum chamber, and then they hit a button, depressurize everything, fire the gun, and then we look at what happened. The other type of facility is an electrostatic dust accelerator. And we went to one in Germany. There's also one in Colorado. There's very, very few of these facilities around the world. But what they do is they take a big electrostatic generator, so something like a Van de Graaff machine. Like, have you ever been to a science center where you put your hand on a big metal ball, they crank something, and it makes your hair stand up on end? Yep. Basically like that. But this is something that can generate 2 to 3 megavolts. And at the positive end of the terminal, what they do is they put a bunch of dust particles inside a canister and they sort of swirl it around so that randomly, once every couple seconds, one of those dust particles will drop out and see this 2 megavolt acceleration. And so they charge up those particles, eject them into the potential well, and they come screaming down the generator. And that's what they can accelerate particles there up to 100 kilometers per second. And that'll depend on the size of the particle. The smaller particles can shoot up way faster. The larger particles can get up to 3 to 5 to 10 kilometers per second. And again, we shoot particles down a tube into a vacuum chamber. We put all of our targets and sensors there, and then we make our measurements.
Mhm. And looking at your profile, you also indicated that you have or working on deployable sensor systems for small satellites. Mm-hmm. So could you talk about some of them, like their purpose?
Sure. So this is part of where my particular unique PhD path, I told you about how I started working on space robots, and then I went into solar sails and CubeSats before I went into impact plasmas and sensors. So when I started looking at sensors for our ground-based experiments that could look at these impacts, it was something that really pulled from the experience I gained developing spacecraft systems in TAing the spacecraft design class or working in the CubeSat lab. And after I finished my PhD, I ended up working in a Caltech lab on deployable space structures. So we were looking at everything from small autonomously reconfigurable space telescopes that use high voltage piezo electrodes to take optical mirrors and reshape them to form different parts of a telescope, to large deployable 60-meter solar concentrators that might be able to like collect solar energy in space 24/7 and beam it down to the Earth in microwaves so that we can have like constant solar power rather than solar power only when it's sunny and when it's daylight. And so working a lot of those mission concepts, coming back to Stanford as a research engineer, we've been looking a lot at low-level technology concepts. So things where if we can do some preliminary work, we can increase the readiness of these technologies. We can envision missions that might not fly for the next 20 or 30 years, but could be game changers down the road. And so one of the things I was looking at was taking some of the lightweight deployable structures work that I did at Caltech and through the solar sail work and combining that with the space environment work I did as my PhD. And one of the ideas was if we want to explore asteroids, let's say we want to, let's say we're a startup company, we want to figure out what asteroid to go to so that we can mine it for materials or figure out which one we want to like drag back to Earth before we do stuff to it. The challenge is we've only visited a very small handful of asteroids in the entire solar system. There's probably millions, at least hundreds of thousands of asteroids out there, either near Earth asteroids or asteroids in the belt beyond the orbit of Mars, which are a lot further away and would take a lot more investment to get to. So we were looking at a concept where we could take hypervelocity impacts. So we know meteoroids hit spacecraft. We know they hit the Earth. They're everywhere in the solar system, so they must be hitting asteroids as well. So if meteoroids are hitting asteroids and are excavating asteroidal material in this ionized form, the same way they do for spacecraft in our ground-based experiments, then could we put a plasma sensor floating around the asteroid and do the same thing we did with our experiments, but look at what the material is that's coming off of the asteroid? So that was one concept that we've been studying is if we can take plasma sensors and put them around an asteroid, that's something that's a pretty lightweight mission. It wouldn't take a very power-hungry, heavy payload the way a lot of the spacecraft or all of the spacecraft that have been sent to asteroids these days are large, conventional, big spacecraft with spectrometers, with large radio instruments, cameras, they've got everything. And because of that, they're expensive. So if we're trying to like explore, let's say, 50 different asteroids to see which one's best, there's no way we can afford to do that with a Hayabusa or an OSIRIS-REx or any of these big space missions. We want to send something small like a CubeSat. And so what is the smallest spacecraft we can send out to an asteroid that will give us something useful about what's on on the surface is the question we were trying to answer. And we sort of coupled that with the stuff I learned from my postdoc, the stuff I learned from my PhD to come up with this mission concept.
Mm-hmm. And what would you say has been your toughest accomplishment so far?
Sorry, could you repeat that?
So what would you say has been your toughest accomplishment so far in your career?
My what accomplishment?
Toughest.
Toughest.
Hardest. Yeah.
Ooh. Let me think about that. There's a lot of things that are tough in very different ways. And so technologically, I think that the thing that's been toughest that I'm most proud of would probably be building those sensors for the impact experiments. So one of the things was we had funding for it, but it was pretty limited funding. And I was using a lot of creativity, a lot of design experience to like build sensors at low cost that actually worked, and they yielded results. That they collected so much data that we're still having students look at some of the measurements I made. And it's been 10 years since we ran those experiments. So technologically, that was a tough experience that I was really proud of. But what was, I think, the most difficult was probably managing our CubeSat program. And this is something that ended up really not ending up the way we wanted. So when I came back to Stanford, this was around 2015, we had a CubeSat program running. And what we were doing was having the spacecraft design class at Stanford. So the master students who were going through the curriculum, they were designing and building a CubeSat that we would be using along with many other universities, many other organizations. Everyone was building a CubeSat that would fly a particular space weather sensor. And the idea for this QB50 program was that we would build 50 different CubeSats and launch them all at once, deploy them off the space station or deploy them off of a rocket. And because there's so many of them, we can make distributed measurements of the atmosphere. And basically, these would be deployed in a very low altitude. They would deorbit very quickly because of atmospheric drag and give us a look at the lower atmosphere where typically we don't make measurements because of the short lifetime that satellites would have. And programmatically, this was probably the toughest thing I've ever worked on, just being able to coordinate with the students in the class, the instructor of the class, the program managers at our funding agency, the other universities working on the program, the launch people, the federal agencies issuing launch licenses. All of that had to come together. And ultimately, we never flew our CubeSat. It's still sitting in our lab. We put everything together. We had it shipped over to where it was going to be integrated with the sensor, and there were software bugs. There were things that we couldn't solve. And so we had to take the thing, ship it from the Netherlands back to California, disassemble the thing. There was a component that was missing that we had to ship over to South Africa for repair. And ultimately, there were so many problems that came up and turnover in personnel that we just never made the deadline and we never ended up flying. Mm-hmm. And so I definitely learned a lot. I think the students who went through the class still learned a lot from that design experience. But it was definitely disappointing having to go through all of that and end up with a CubeSat that's sitting on a lab bench and not one that's actually flying in space.
And what is a big milestone that you're looking forward to in your research?
A big milestone. Well, one of the things that I'm doing that's new is starting in January, I'm actually going to be instructing this spacecraft design class, the one that I TA'd back in the day with the solar sail work, and that was working on this QB50 spacecraft. So for the next 6 months, I'm going to be able to take the class and make it sort of my own. And having seen all of these different versions of how the class was run, I'm pretty excited about how that's going to go. And I'm also pretty nervous about it because it's going to be the first time I'm actually the primary instructor for a class. I've done guest lectures, but I've never actually taught a class before. And what I'm really excited about is if I can make this class work well, I really want to start pulling the class projects in to the research that I'm doing. Right now, it's sort of separate. I'm sort of keeping the class pretty self-contained, partly because with the way the pandemic is going, we just heard that we're going back to 2 weeks of remote learning. So trying to teach a practical hands-on class while all the students are not in lab is going to be a big challenge. But what I really want to see is have this class be successful, have the students be able to design things that actually fold back into the research programs that we have. And hopefully that'll happen in the coming years.
Mm-hmm. And to high schoolers like me and to younger generations that want to become aerospace engineers, what will your advice be to be successful in this career?
That assumes that I'm successful and know what I'm talking about. One thing that I really want to emphasize is that only you can really determine what success means for you. I was told as a PhD student, as a postdoc, that I really should be faculty. I should become a professor. I need to do that to be successful. Otherwise, like being a research engineer, being someone who's not tenure track at a university, it is not the usual goal for a lot of students, nor a lot of academics, but it's what works for me. I like working with the people I get to work with. I like having the freedom of academia. I like having the flexibility of driving my own projects, but not being tied down by all of the things that professors have to do. So I'm where I want to be, even if it's not the place that most people say is where a successful researcher should have ended up. So that's one thing, is know yourself, know what you want, and make that work for you. Don't let other people tell you that what you should be doing is X and end up being miserable in a place just because someone said you would be good at it, or that's what success means. The other thing I would say is just keep learning and stay curious. So a lot of where I had my best successes was because of prior experiences that I was able to pull into the current problem at hand. So when I had to design a plasma sensor for this experiment, I knew nothing about plasmas, but I knew circuits, I knew PCB design because of my CubeSat experience. So I was pulling in knowledge from, like 5 years before, I was pulling in knowledge from my robotics research, and pulling all of that together to make my PhD work. And the same thing's happening now with the new concepts and the new proposals we're writing. We're always pushing towards things that we don't know where it's going to really end up. And the important thing is, even if you're facing a problem that's unknown, there are parts of it that you can pose in a way that makes more sense to you, that you've seen before. You can take something that looks mysterious and figure out the different parts of it and how they work based on stuff you've already learned. And in order to do that, you have to sort of be creative. You have to pose the problem in certain ways. You have to remember what you've learned in the past to be able to use it. So just be excited about what you're learning about, and keep learning. Keep filling your brain with all sorts of stuff, whether it's maybe history, maybe it's science, maybe it's culture. Like, all of that stuff makes you unique, and that's what makes you best suited to do what you want to do. And I think that applies to whether you want to be an aerospace engineer or anything in life. Is you have to be true to yourself.
Mm-hmm. All right, well, thank you for joining me, and thank you for letting me interview you. That was great.
Thanks for having me on the show.